Hi, good morning, everybody. Welcome to Papalim Physics Classroom. Okay, today we will be going through one of the MCQ paper for CHIJ prelim paper. Okay, now for this paper, I will be going through most of the questions. So it will be a long video. So if you have attempted the paper already, you want certain certain explanation or certain answer to certain questions, we just remember to drag directly to just skip the video to the correct section that you want. Okay, you don't need to watch from the start to the end. Okay, same as before, if you have not seen this paper before and you'd like to try, okay, I leave the soft copy in my Google Drive. The link is in my description panel below. Okay, feel free to go and download and go and try it out. Okay, it's definitely a good paper. Okay, it's worth your time to actually try it. Okay, now, without delaying, okay, I will look at the question number 1. Now, for this question, right, for those who tried, okay, I actually listed out some of the interesting questions that students may want to take note of it, which is quite interesting. Now, for those who have done it, okay, you might want to pause the video to check your answer, okay, to check what are the careless mistakes they might make, or maybe anything that you want to touch up. Okay, if you're done with the answers, okay, let's proceed to question 1. Question 1, base units, the basic 7 base unit that we have. Okay, this one I will not do too much. All physics students actually should know about this. Okay, so just take note of it. Now, question 2. Question 2 is a vernier caliper, which I believe most of us, when you revise, you definitely know how, you definitely have revised how the readings of vernier calipers, micrometers, and their respective positive and negative zero errors. Okay, if you have forgotten how to read vernier calipers and micrometer screw gauge, I will actually leave a revision videos on the reading of these two instruments in the top right hand corner of the video, so they can actually take a look at it. What is interesting in question 2 is the use of the word diameter and the use of radius. Answer that we're looking at for the reading from the vernier caliper will be 3.2, and the number you are looking for is actually this line. Okay, it will be 3.26 cm. Okay, this is the reading that you read from the vernier caliper, but this is not the answer this is not the answer. Okay, because the question asks for the radius. What you are measuring is actually the diameter, and we all know that radius is actually half of diameter. Okay, so with this answer, you need to divide by 2. Okay, so this is a slightly tricky thing that students you might want to take note of it. So that's why my answer is actually 1.63, not 3.26. Okay, because they are looking for the radius. For question 3 is a micrometer screw gauge. Okay, if you need a short revision of micrometer screw gauge, I left the video in the video link on the top right corner of the video, so you may want to take a look at this particular revision of micrometer screw gauge. Okay, if not, most of you should have the answer. Is actually question 2, B. Okay, question 4 is the interesting one. Question 4, we're looking at velocity time graph, and interesting enough, there is actually a negative quadrant here, negative segment here. Okay, if you're looking at velocity time graph, you'll find that the area under this graph, the positive section here, this will be the displacement for this particular section. If you look at the area under the graph, this will actually give us the area, which is the trapezium. Okay, 24 plus 20 times 4. This will give us exactly what we call 88 meters. Okay, so this is the displacement. Interestingly, is that the negative area here. Okay, the negative area here, this negative distance, okay, if you work out the area, it will be actually 8 meters. This displacement 8 meters, it actually tells us that the object actually has made a U-turn. Okay, it actually went back, it actually moved backward 8 meters. Okay, so in terms of direction, it's actually opposite, okay, to the first 24 seconds. Okay, but the question is asking for this average speed. And we all know that average speed is actually the total distance divided by the total time. Okay, in this case, when we talk about total distance, it's the actual distance that the object covered. Okay, it's not displacement. So the total distance the object actually covered, okay, or the cyclist covered, is actually 88 meters plus the extra 8 meters that he covered when he walked back or when he cycled back. Okay, 8 meters. So total distance he actually covered is actually 96 meters. And the time taken for the entire journey will be actually 28 seconds. 28 seconds, yes, correct. 28 seconds. You'll find that with the total distance of 96 meters, okay, you'll find that the average speed that he has is actually 3.43. Okay, so here the marker is trying to highlight to students to set a distinction between what she mean by displacement and distance. Okay, distance, remember, distance is the actual distance covered by the cyclist itself. Okay, it's not how far you are from the starting to end point. Okay, so just take note of it. So for this case, it will be 88. The total distance traveled by the object, by the cyclist is actually, okay, 88 meter plus 8 meter, which is 96 meter. Now, as for total displacement traveled by the cyclist is actually the 88 meter minus 8 meter. Why minus 8 meter? Because during the last 4 seconds, the cyclist actually made a U-turn and reverse his direction. He traveled 8 meter back, okay, in the opposite direction. So total displacement traveled actually, total displacement traveled by the cyclist is actually only 80 meters. Okay, so this is the distinction between displacement and distance. Now for question 5 is, although it's a short question, but the question 5 is actually quite a tedious question. So far I don't have any shortcuts to it. Okay, so if you happen to have a shortcut, a faster method than mine, okay, please let me know, okay, so that I can share with my students. Okay, if not, this is how I actually do it. Okay, now based on the information given is I need to find the density of the liquid. So which means I need to have the mass of the liquid X, and I need to find the volume of liquid X. These are the two things that I need. I want to bear in mind I need these two. First thing first, the full water bottle, full water is 200 gram. Empty bottle is actually 100 gram. So with these two information, I am able to identify that the mass of water used is actually 200 minus 100, which is 100 gram. Okay, that's the first thing. And based on the question is that the density of volume, the density of water is actually 1 gram per cm cube, which means that indirectly the volume of water, okay, used is actually 100 cm cube. This is important information. This information is important because at the later part, the question actually tells us the same bottle is actually filled with liquid X, meaning they are using back the same bottle, which means that the volume of water, which is 100 cm cube, is actually information that this is actually the volume of the bottle. Okay, which means that at liquid X, at the second instant liquid X, this volume is the volume of liquid X used. Okay, which happens to be the volume of X. Okay, so in this case, I actually have the first number already. I actually have my denominator, which is 100 cm cube. Now, how to find mass of X? Now, based on the question is that the mass of the bottle with X is actually 180 grams. And we know that the empty bottle is actually 100 grams. So with these two information, I am able to derive that the mass of X being used. Remember, the mass of X is X plus bottle is 180, empty bottle is 100 grams. So I will know that the mass of X is actually 80 grams. So which means mass of X, my numerator is actually 80 grams. Okay, so now I have the mass of X and the volume of X. If I put them in the formula, density of X should be 0.8 gram per cm cube, which my answer is B. Okay, for this particular questions, I have to find each component part by part, step by steps. For MCQ question, I find it's actually quite tedious, although the concept is actually quite simple. It's definitely a good question. Okay, question 6, you have vacuum, so we are looking at free fall. Okay, free fall without air resistance, so it brings us to this velocity time graph. Okay, so let's say I have it takes me t seconds to cover a length of L. So let's say for this, let's say this is t second. Okay, so this is t second. So this will be let's give it vt. Okay, let's give it v. Okay, let's say this is v. Okay, now based on the information is that at t seconds, the object actually the feather actually travel a distance of L. So indirectly, I'm saying that the area under the graph for this segment here is actually L. Distance, remember kinematics, okay, is area under the graph, which is half vt, which happens to be L. Okay, now the same vt graph, now the question asks, what's the distance traveled by the feather at 0.5 t? Now at 0.5 t, what actually happened is this. At 0.5 t, okay, at 0.5 t, this is what happened. Okay, at 0.5 t, because the line is a straight line, it's a constant gradient. So at half the t, I will definitely know that the speed traveled will definitely be half the velocity. And the question asked is, what's the distance traveled? It will be definitely the area under the graph here, which is this small triangle here. Okay, so distance traveled in the 0.5 t, okay, will be the area under the graph, which is half base is 0.5 t times height, which is half v. Okay, and if you look at the mathematics, okay, you'll find that this particular number, half vt is actually L. Okay, so indirectly, I actually can replace it with half, and the half vt, I can actually replace it with L. Okay, then after that, if you simplify the question, it will be 1/4 L, which is happen to be 0.25 L. Okay, so the distance traveled will be 0.25 L. Okay, so what I've done is I use the mathematical approach to solve free-fall questions, riding on the fact of they all have the same velocity time graph. Okay, so this is how I will approach this particular question using the basics of kinematics graph. Okay, which is something that every student should actually be well versed in it. Now for 7, okay, 7 is the turning effect. Okay, moments. What's the resultant moments? I remember what's the resultant moment means. I'm looking at the total moments. And this question, this is the pivot. And if with P as the pivot, you will find that there is actually 3 moments we are looking at. In this case, the 20 Newton will actually provide a clockwise moment. 15 Newton will actually provide a clockwise moment. But the 10 Newton will actually provide an anti-clockwise moment. Okay, so let's look at each of the moment carefully. Okay, so at 10 Newton here, at 10 Newton here, the perpendicular distance for 10 Newton, okay, which is the distance from the force to the pivot itself, which is actually your 3 meter. Okay, so moments of 10, okay, the anti-clockwise, it will be the force times the perpendicular distance, which will give us 30 Newton meter. Okay, now similarly for similarly for 15 Newton. For 15 Newton, the force, the line of action is here. The perpendicular distance I'm interested in is actually from the line of action to the pivot itself, which is 2 meters. So which means the moment by 15, it will be 15 Newton times the distance, which is 2 meters, which will give us 30 Newton meter clockwise. And similarly, if you look at the 20 Newton force, okay, 20 Newton force, okay, you'll find that the perpendicular distance will be here. This is the line of action of the 20 Newton, okay. So the perpendicular distance here will be 2 meters. How do I know it's 2 meters? Because I know that based on the question, this is 4 meters. 3 plus 1 is 4 meters. So it's on top is 2 meters. I will know the bottom will be 2 meters. So it will be 20 Newton. It will be 20 Newton times 2, which will be 40 Newton meter. And if you add up all the forces, including the directions, 2 anti-clockwise, okay, 2 clockwise moment and followed by anti-clockwise moment, okay, you will have a resultant moments, including factoring the directions. You will end up with the answer 40 Newton meter. Okay, quite easily done. Okay, just taking note of the perpendicular distance. So do not take any distance like anyhow you want. Remember, concept of moment is the perpendicular distance that we are interested in. Question 8. Most stable arrangements. Usually what we have is broad base, low CG. Definitely one look you will know. It will be B. Now, 2 identical flasks for number 9. After that, the valve is open and the water will just stream over. So by default, I would say by deduction, you'll be able to know that the final outcome will be that water will be shed evenly across the two vessels. How much is the mass? You will know that it's actually half mass here. It'll be half mass here. Okay, and what's the height that you're looking at? Is half of the height here also. So everything will be half because it's shared evenly by the two vessels. Okay, how much of the water is lost? Okay, so in fact, okay, if you look at the loss, I would say that this amount of water actually originated from this area. Okay, so which means the energy loss at the blue color one will actually be equal to the energy gain at X, at Y here. Okay, so energy at Y here will actually be your mgh. Okay, you lost the amount of potential energy. Okay, energy gain is equal to energy loss. So you lost this amount of height, okay, which is half a h. And you lost half a m of mass here. So it will be half mass G and H. H will be half of H. So if you work out the math, it will be 1/4 mgh. Okay, so which means you actually lost 1/4 of your energy. Okay, remember, whatever energy you lost is actually the energy gained by vessel Y. So gain and loss, they are actually equivalent. So the energy loss, okay, is actually 1/4 mgh. Okay, so just take note of the mathematical manipulations. Now, then after that, we bring us to question 10. Okay, now question 10, the key information here is at 76 cm Hg. For X, pressure X here, pressure X here. Okay, pressure X is actually due to pressure of the water above it, which is the 15 cm. Okay, plus the pressure of air that's above it. This is the pressure. So this is, if I can find the two of them, I can find the pressure in X, which is what the question is asking for. Okay, now 15 cm Hg. So far, I know is for 15 cm is definitely cm Hg. That's the pressure, but I do not know what is the pressure in X. Okay, so I have a missing column here. Okay, so I need to find that missing thing. Okay, but the other information that's given to me is that there is actually a pressure, the atmospheric pressure. So which means 76 mm, which is actually here. This is my 76. Okay, atmospheric pressure is actually equivalent to this particular point. And this particular point, the pressure is actually what is above it. So is this pressure experience is from the amount of liquid here, mercury here, including the air. So it will be P, what's the height? 70 cm plus P air. Based on the question, you have 76 cm Hg. P70 is actually 70 cm Hg. P air unknown. But with this equation, I can actually simply work out that P air is actually 6 cm Hg. So once I identified P air is 6 cm, I can actually substitute inside here 6. But this is what I want. Okay, so this is your 6 cm Hg. And now my P air is no longer unknown, so I have actually found a number. So the total pressure for Px is actually is doable. Okay, so it'll be 15 plus 6 will be 21 cm Hg. Okay, quite easily done. Okay, so with this, you will find that the pressure at X is actually 21 cm Hg, which is answer is C. Okay, so one thing to highlight again to students, you must remember pressure when looking at liquid pressure or fluid pressure, to be exact, air and liquid. You must remember that pressure actually exerts from the water level or from fluid that is above the particular point, okay, above it. Okay, so this is one of the important things that we have to take note of it. Question 11. Question 11 here, we're looking at temperature. Okay, one of the easiest way that I like to solve thermometer question is to use proportion. Okay, so what we are looking here is actually there are 40 cm here. But this 40 cm actually control a temperature difference of 120 degrees Celsius. 120 degrees Celsius, okay, just to take note, because I have a range of 110. I have the smallest range 100 and my -10. So the total temperature difference is actually 120 degrees Celsius. And if you look at the question, if 40 cm controls 120 degrees Celsius, if I have 20 cm, half of it, I should actually control 60 degrees Celsius temperature intervals. So indirectly, I'm saying that this number here and this number, the interval here should be 60 degrees Celsius. And if I know that the interval on the left is -10 degrees Celsius, and I know the difference between them is 60 degrees, and indirectly, I actually would know that this is actually 50 degrees Celsius. Okay, because the difference between 50 and -10 will give me exactly 60 degrees Celsius. So that's why I know that the answer for 11 will be actually B. Okay, the temperature at that particular point at 20 cm is actually 50 degrees Celsius. 12 is a standard definitions. Okay, when you look at heat capacity, we are looking at the vibrations. We are looking at the vibration of the molecules. So the energy needed, the energy that is given is actually to increase the vibrations of the particles. Okay. Potential energy, remember, potential energy is, it has to do with energy state change, okay, breaking the intermolecular bonds or reducing the intermolecular bonds so as to change of states. Okay, so it has, so it has nothing much to do with heat capacities. Okay, now question 13. Question 13 is, there are two objects that we're looking at. Okay, now you have ice at melting point. Okay, so if I draw a heating curve for ice, okay, so let's say this is 0 degrees Celsius. Okay, so this ice. Okay, so this ice, this temperature, this time. So I have a temperature graph for water. Okay, so this is temperature, so this is water. Okay, so what happened is we're looking at, let's say for ice, I'm looking at ice at melting point, ice at melting point, ice at melting point. Okay, melting point, ice at melting point means I'm actually at this particular stage here. Okay, so this is where I am now. Sorry, okay, this is where I am now at this particular section. Then what happened is when I drop into my water at 15 degrees Celsius, so my water actually 15 degrees Celsius, it will be at this stage here. So this is 15 degrees. Okay. Now, when I drop the two of them together, you'll find that the water will actually cool down because of ice. So which means the water will actually cool down. It will still remain as ice. So the new location will be here. So I call it theta. Ice, on the other hand, if I put inside the water, which is slightly warmer, my ice will actually start to melt. And eventually, both of them will actually approach same temperature, theta. Okay, this is what is happening. All right, so the two theta are actually the same number. It's just that the ice is heating up, the water is cooling down. Okay, so they will meet in the middle of theta temperature. And what we have is conservation of energy. The energy loss, the energy loss, and the energy gain is actually the same. For ice, it will be energy gain. And where does the energy come from? It comes from the water losing the energy. Okay, and in this case, the water we are looking at is for water. It actually loses this particular amount of water, which is controlled by MC delta theta. So your mass of water, heat capacity of water, okay, multiplied by the change in temperature of water. Okay, change in temperature of water, please be careful, is actually higher temperature minus lower temperature. So it will be higher temperature will be 15 degrees Celsius minus temperature theta degrees Celsius. Because remember, when ice is dropped inside the water will actually cool down. Okay, so 15 degrees Celsius will be the hotter temperature. As for the ice actually goes through two stages. One is the melting phase. He must melt first. So which means the melting will be latent heat of fusion, which is mass of the ice plus the latent heat fusion of the ice. After melting, it doesn't end there. The ice will have to heat up a small particular section here. Okay, now ice has melted, so it is water already. Okay, but of course the mass is the same lah. Okay, so in this case, I will use mass ice to denote lah. Okay, so this is mass of the ice. Okay, but in this case, it's water already. So heat capacity will be water plus the temperature of the plus the change in temperature. In this case, theta is actually the high temperature. It comes from 0 degrees Celsius. So it will be theta minus 0 degrees Celsius. So true enough, if you rearrange the mathematics, okay, so let me rearrange a bit. Okay, let me rewrite a bit so it's not so confusing. So it'll be theta minus 0 degrees Celsius equal. Okay, so now if you rearrange and you substitute all the values inside, mass of ice, you know, is 0.1. Okay, mass of ice is 0.1. Latent heat of ice given is 336,000. Okay, and the same ice is here, and the same ice is here. Okay, the same water has melt, ice become water, so it's 0.1 kg. Latent heat of water is given 4,002. Okay, multiplied by theta, it will be equal to water. So now how about water? Water, based on the question, water is 0.8 kg. So mass of water is 0.8 kg. Latent heat of fusion, the specific capacity of water is 4,200. So this will be 15 minus theta. So if you solve the algebra, you solve for theta. Okay, you will have the answer to be C. Theta will be 4.4 degrees Celsius. Okay, so this is how I look at it in the question here. Okay, so far I do not have like a nice way of solving it, a shorter way of solving it, but I do understand that there is actually a shortcut in it, whereby you look at proportion. But I just that I find that proportion method, that shortcut, sometimes it just lead to a rough range of answers. It may not give you the exact answer. So example, if I use that proportion answer, it will end up, I will definitely end up with like the answer to be in the range of B or C, 8.8 degrees Celsius or 4.4 degrees Celsius. I will not have any means to narrow down to which is the correct answer. But nonetheless, if you actually have a shortcut for this, because I find that my method is actually quite long, too long. So if you have a shorter method, please let me know so that I can actually learn something from it, where I actually can tell my students to take note of this particular your particular approach. Thank you very much. Okay, for question 14 is on thermal heat property. Okay, we are looking at these two objects of different specifications. Now, one thing to take note is for this question, you'll find that the heater for both of them, okay, the power used to heat, okay, is actually the same. So we can actually rephrase the question to be power of P is actually equal to the power of Q. The power of Q given and power of P is actually the same. Now, for in both cases, we are dealing with solid, heating up of solid. So the formula that we are dealing with will be MC delta theta. Okay, so left-hand side is P, right-hand side will be Q. And based on the question, temperature change in Q is given, temperature change in P is given. Okay, so the left-hand side will be 20, the right-hand side will be 40 Kelvin. Then on the other hand, mass of P is given, 0.4 kg, mass of Q is given, which is 0.2 kg. Okay, so this is 0.2 kg. So MP is 0.4 kg. CP is not given. Specific capacity of Q is also not given. But if you look at the math, I can get a ratio of CP over CQ. Okay, so I can have a ratio of these two numbers, and you find that the math will work out to be actually a perfect one. Okay, in this case, based on the mathematics, you'll find that CP, specific capacity of P and Q are actually the same. Okay, they are actually the same material. Okay, so in this case, CP and CQ are actually the same, which means that option C and D will be wrong. Okay, neither of them are actually half of each other. Okay, because they are actually the same. So in this case, how about the option A and B, where we're dealing with heat capacity? Okay, so take note of the mathematics for heat capacity. Okay, big C. Okay, it's actually equal to M small c, product of mass and the specific capacity. In this case, you actually have two items. Okay, so you actually have P specific heat capacity of P if you product of mass of P times specific capacity of P, and vice versa. Q will be Q and Q. Okay, so in this case, you'll find that the mass of P is actually 0.2. And for Q is actually, for specific capacity of P, for the mass of P is actually 0.40. And the mass of Q is actually 0.20. Okay, in this case, because CP and CQ is the same, so they are actually the same number, so there's nothing to compare. So which means indirectly, I'm saying that you'll find that based on the mass, you'll find that the heat capacity of P is actually twice the heat capacity of Q. Okay, because one is 0.4, while the other one is 0.2. Okay, and with this, you will actually narrow out down to the answer of option B. Okay, whereby the heat capacities does make a difference. Okay, because of the mass. Now for option 15, you are looking at transfer. Okay, particularly here, I think it will be more for radiation. Okay, take note is that the left side is the hot. Left side is the hot liquid. So remember, we are looking at hot transfer heat from hot to cold. So it will be from heat transfer direction will be from the left to right. So in order to reduce heat loss, what I'm looking at is I'm actually trying to reduce the radiation here. And I'm also trying to reduce the absorption here. Okay, and I also want to reduce the radiation here. Okay, because if I can reduce the radiation absorption at the correct position, okay, I will be able to reduce the heat loss by radiation. So in this case here will be radiate less. Okay, this side will be radiate less. And in this case, this area here will be absorbed less. Okay, this side here. Okay, so these are the specification I need for these three areas. So between Q and S, I should want it to radiate less, and R, I should actually want it to absorb less. Okay, and based on the pattern here, I will say the one that matches your answer will actually be option D, because white surface is definitely a bad absorber and a bad emitter. Okay, black is a good absorber and a good emitter. Okay, so if we're talking about reduction in radiation, we are looking at white surface or maybe shiny surface. Okay, so these are the two surfaces that I might want. So that's why I will choose option here to be D. Okay, 16, one of the idea of having a red towel across it is because of evaporation. Okay, the evaporation from the cloth. Okay, the evaporation from the cloth. What happens is when you put the wet cloth over the drain, okay, the water evaporation from the cloth, okay, will leave behind what we call a cooling effect. And as a result, okay, the cooling effect will actually cool down the water bottle that's below the towel itself. And of course, because I want the process to be continuous, I want it to be like a continuous evaporation to be taking place, continuous cooling. So that's why I actually put some water here, okay, so that the water will be absorbed to the cloth, okay, whenever evaporation takes place, to actually restock the water level in the cloth, okay, to ensure evaporation actually take place continuously. So answer actually is D. Okay, evaporation to cool down the drink itself. Now, for 17 is 18 with roughly the same idea, whereby we're looking at the power. Okay, the power of both of them is actually the same. Okay, so in this case, we are looking at power is actually energy divided by time. And in this case, power is actually MC delta theta divided by time. Okay, and based on the graph for energy temperature time graph, one of the interesting fact there is that the delta theta divided by time, this fraction here happens to be the gradient of the temperature time graph. So this is a slight trick that we have to take note. So actually by looking at the gradient, I am able to compare what are the information, what information am I looking at. Okay, now since X and Y are having the same power, so inherently what we are looking at is that we can compare X and Y. Okay, so Px, it will be mCx, okay, delta theta over time. Okay, this X, or what I call gradient of X. In this case, it will be Y, my, cy, and this will be delta theta divided by time. And this one will be the gradient of Y. Okay, remember, this vector here is the gradient of the graph itself. So this is the gradient of X, this is the gradient of Y. Okay, so in this case here, let's take a look at the gradient. Now, you'll find that since the power is the same, which means the left-hand side is actually the same. Okay, this left-hand side is actually constant. Okay, so this is actually constant. Let's look at the X first. Okay, so for line X has a steeper gradient. Okay, line X has a steeper gradient, so which means the X here, this gradient delta theta over T is actually a big number. Okay, and in this case, we know that okay, they are of equal mass, so the mass is not going to affect anything, because both of them actually has the same factor. They are equal masses. Okay, so on the other hand, what happened is that the gradient of Y is actually a smaller number. Okay, so in this case, for left-hand side to remain constant, for the Px and Py to remain the same value to be constant, you will find that my specific capacity of X has to be a small number, such that the product of these two will become the constant number. And vice versa, my Cy has to be a big number, specific capacity of Y has to be a big number, because the product of both of them has to be a common number again. Okay, so you find that based on this analysis, you'll find that Cx is actually smaller, okay, than B. Okay, Cx has to be smaller, Cx has to be smaller than Y. Okay, the specific capacity of X has to be smaller than Y, which means that the option C, okay, is actually the answer. Because in this question, the question asking for which of the following question is incorrect. Okay, so the idea here will be, okay, C is incorrect because B is correct. Okay, so this is what we mean by looking at the answer. Okay, in this case, I will judge based on the gradient first, as in it happens that the more I analyze, okay, it happens with C will give me the answer. Okay, so vice versa, if you look at latent heat of fusion, you can look at it in terms of liquid phase 3. You can look at this level here, the phase 3, comparing of X phase 3 is liquid, and the phase 3 of Y, okay, by repeating the same process again. Okay, in this case, instead of looking at it as the solid heat capacity, you are looking at specific capacity of the liquid phase itself. Okay, so just take note of how I use mathematics to solve this particular question. 18, melting point. Okay, melting point. Which of the following quality does not change? Take note, it does not change. Does not change when I heat from 0 to 100 degrees Celsius, 110 degrees Celsius. Which of the things does not change? Okay. Density, kinetic, internal energy. Internal energy, take note, internal energy includes kinetic energy plus the potential energy. So the moment you have a change in state, the potential energy must change. There's a change in state. Okay. And even if there isn't any change in state, let's say, for example, in this case, there isn't a change in state, but because it's ranging from 0 to 110 degrees Celsius, which means the kinetic energy of the item itself, the energy of the material is actually increasing. And with EK or KE increasing, internal energy will increase. Because internal energy consists of two components. One is EK and one is EP. Okay, so just take note of this. And of course, when you talk about heating, whenever you heat, there will definitely be expansion. Okay, so when you expansion, volume increases, you talk about density will change also. So the only one that will not change is actually what we call the specific heat capacity of the material itself, because this is actually targeted at the material at the phase itself. Okay, so that's why the answer is D. Question 19. Question 19 is refraction and critical angle. Now take note of the critical angle. Critical angle is only happens at where? Okay, dense to less dense medium. So same thing, okay, when we're looking at this particular angle of refraction, to be exact, is here. Okay, this angle of refraction, and this is the angle of incident I'm looking at. Okay, remember, angle of incident and refraction has to be measured from where? From the normal to the ray itself. From the normal to the ray itself. Okay, and we always look at it in terms of refractive index is actually sine of the angle in the less dense medium divided by the sine of the angle in the dense medium. And in this case, this is glass block. This is air. So air will be the less dense medium. Okay, so in this case, it will be sine I over sine R, which is sine, okay, 33 degree divided by sine R. Okay, refractive index based on the question is given is 1.5. Okay, so with this particular formula, you should be able to work out the answer of sine angle R, okay, which happens to be 21 degrees. And vice versa for critical angle. Critical angle, we have one formula. Okay, critical angle is sine critical. Okay, is equal to the critical angle is equal to 1 over refractive index. And you work the answer out, you will get 42 degrees. So that's why I will know the answer is A. One thing to caution students is, okay, you must remember the angles of I and R actually is measured from the normal, okay, not from the horizontal surfaces or not from the surfaces. Okay, take note of the small things. And similarly, you will find that, okay, the same idea will be propagated to question 20. Yeah. Okay. Now remember, for critical angle or internal reflection, it is always from, when we're looking at it, is always from dense to less dense. From dense medium to less dense medium. So we are looking at dense to less dense. And for in this question, your P is less dense medium, Q is actually dense medium. So when you're talking about less dense to dense, you only got one answer only, which is the ray must exit and it must bend towards the normal. Okay, because it's dense to less dense. It must bend towards the normal, it must exit. There's no critical angle, there's no total internal reflection. Okay, because it bends away, it bends towards the normal. So that's why I know the answer is actually 3 only. Okay, so take note, don't be tricked, okay, by the question, okay, because in this case, you must know all the basis. For critical angle, okay, it's always from dense to less dense, okay, or even the total internal reflection. Now, for question 21 is a common question, okay, whereby you need to know the technique. Okay, I will run through this technique again. Okay, it happened before in the previous paper, as in like 2021 last year when I analyzed some of the prelim question. Okay, now, rule of thumb is to take note of the wave direction. So it's going from right to left. So which means that the wave at this instance, it look like this. At another short interval, let's say 0.5 seconds later, because the wave is going to the left, so it literally is moving to the left. So the wave will look this way. Okay, so which means that originally, okay, the point, the dot, this P is here. So the next instance, the P will actually take on a new position, will be just, okay, take on new position. He will be just here. Okay, he has moved up to become the new location. And similarly, originally Q was here, and now at the new location, Q actually moved downwards to occupy this space to actually form up the new waveform. Okay, so when the wave is moving from right to left, although we see a slightly different waveform, but actually it doesn't mean that the particle actually has moved left or moved right. It actually just means that the particle is now vibrating at another position, at new position. It's just moving up and down at different location at different timing. So for this case, while the wave moved left, okay, you'll find that Q move down, Q will move down, while P will move up. Okay, so what happened is P will move up, okay, Q will move down. So that's why the answer here is B. Okay, so take note of how I identify the movement of the particle itself. What I usually do this is that I look at the new wave location, and from the new wave location, I will be able to identify the new particle location. Okay, it's either like along the straight line, because why? Because particle is always vibrating at that position. Okay, at that interval, it doesn't move away. Okay. Now, question 22. Question 22, I would say is classic example of V equal F lambda, your wave formula. Okay, it's just that in this case, you'll find that this is your wavelength. This 2 meter actually is denoted by actually one wavelength and another wavelength. So I can safely say that there's actually 2 wavelengths occupying this space. And because 2 wavelengths occupy 2 meter, and you will find that actually one wavelength is actually 1 meter here. Okay, one wavelength is actually 1 meter, which is either to answer. Now, what happens is when the frequency is half. This is one of the things that students have to be careful. Now, one thing you ask yourself is, while the frequency is half, okay, the wave is still moving at the same place. The wave is still moving at the same medium. So in other words, is while the frequency has half, okay, the medium remains the same. Okay, it's still at the air location. So when the medium is the same, okay, when the medium is the same, it will actually tell us one important information. It means that the velocity of the wave itself, or the speed of the wave itself, is actually remaining the same. Because speed of the wave actually depends on the medium itself. Okay, different medium, yes, the speed of the wave will change at different medium. But just that if the wave remains in the same medium, the speed is controlled by the medium. So the speed of the wave in that same medium is actually remaining the same. So in other words, is that despite my frequency being half, my speed actually remains the same. So it's a fixed number. So it remains the same. So in other words, is that for me to have the same speed at the half the frequency, one important change must happen is that the wavelength actually must double, okay, to get back the same speed. So which means for the same speed to reach point A, point B at the same speed, okay, when the frequency of wave actually decreases, what each of the wave must do is they actually must be longer, okay, so they cover more space. So which means the wavelength originally was 2 meter, originally was 1 meter, the wavelength must double, okay, must double, and that's why the new wavelength is actually 2 meter now. Okay, not half or not 1 meter. It actually had to be double, which is 2 meter here. So that's why I know the answer is C. One of the information that we always like to play around, or we like to trick students, is by looking at the medium. More often is that you'll find that actually students tend to think, hey, the frequency of the wave should actually remain the same, and it should always remain the same. It will not change. This statement is not correct because it depends on the situation. Sometimes it's that the wave medium will change, and as a result, the speed of the wave will change also. Okay, and because the wave changes, the frequency, the identity of the wave actually remains the same, because that wave I have not tweaked its frequency, is already in the transmission already. So that's why the frequency remains the same. But on the other cases is that when I uses the same medium, so the factor that I tweak is I tweak the frequency. I tweak the type of wave, the frequency of the wave, the pitch of the wave, so that the same wave will actually, the same speed will actually be transmitted across the same medium, but just that the frequency of the wave actually changes. So students, you have to take note of what is actually changing. Okay, whether is the medium the same. Usually we tend to take that if the medium remains the same, okay, the speed actually remains the same, in the sense that speed of the wave is dependent on the medium itself. Okay, so this is one thing to take note. Now for question 23 is fairly simple. 23, okay, 23 23 is a classic example of electromagnetic spectrum, so I will not dwell too much. So students, you need to remember the spectrum, what are the wavelength, what are the arrangements, what are the users, okay, and what is the frequency and wavelength of red light, green light, okay, and what are the wavelength and frequency for microwave, gamma ray, X-ray, all these things. Okay, same thing. Now, 24 and 22, I would say is the reverse of each other in the sense that now instead of having the same medium, I actually changes the medium. Okay, so this is from water to air. Okay, so now water to air, this is dense to less dense. Okay, now dense to less dense, what actually happens in this case? Okay, same thing like I mentioned, now the medium changes. So which means the frequency of the object and the frequency of the wave actually remains the same. Okay, so D is out already. Okay, so the frequency remains the same. So this is constant. And vice versa, okay, I uses the speed of the wave speed, so which means this is constant. Okay, so what happened to the lambda and what happened to the speed itself? Now, same thing is, you'll find that because of the way the formula is structured, you'll find that with frequency constant, V and lambda is actually proportional to each other. Okay, so now here is the trick that you must remember. Now, the trick here is we are looking at sound wave, not light wave, not EM wave. If you look at EM wave, okay, EM wave travel fastest in less dense medium. Okay, it travel the slowest in solid, in denser medium. But for sound, okay, for sound, remember, sound is the reverse. Sound actually travel fastest in solids, slowest in air. Okay, because of the molecular structure. Because in solid, the molecular structure are closely packed together and they are able to transmit the vibrations, refraction, compression at a faster rate. So that's why in solid, sound is actually traveling a faster time. So in this case, when the sound travel from water to air, it means that the wave of the sound actually slow down. And with this, we know that if V and lambda, velocity speed and lambda is actually proportional to each other, you'll find that if my speed decreases, it will imply that the wavelength of the wave actually has decreased already. So in this case, you will find that speed is reduced. This is what I need. Wavelength reduced. Okay, so with this, my answer here will be A. Okay, so this is how I use the wave formulas. I use the property of gas, of sound and EM wave, okay, to actually look at answers scenario whereby it's looking at whether the first scenario, whether the frequency changes but medium remain the same, or second scenario, I'm looking at medium changes but frequency remain the same. So these are the two common situations that will happen for waves. Okay, be it EM waves, transverse wave, or longitudinal waves. Now for 25, before disturbance, after disturbance, you'll find that the P is the one that doesn't change its position. So it's one of the crucial point. Q will still remain the same, and you'll have this particular point which is remaining the same. Okay, so these are what we call the fixed point, which means that they are always at the equilibrium. So by looking at the particle beside them, okay, you'll be able to deduce whether this is refraction or compression. Example, for P, you look at after disturbance, you find that the dots are actually going closer together to P. So which means I can say that P is actually what we know as your refraction, and Q will be your compression, and vice versa, this point here will be your refraction here. So which means one thing to take note is that between PQ, the common thing that we need to take note is between this point is actually one wavelength. Or aka between R and C is actually half a wavelength. Okay, so between R is actually half a wavelength. Okay, and what happened is RS is this particular dot. Okay, and now it's here. So just now the location was here, equilibrium was here, and now this R is actually here. So this is how much the particle has vibrated. And this is actually what we know as the amplitude of the particle itself, how much it has vibrated. So this is what we mean by your amplitudes. That's why my answer here is A. Okay, so just take note of how you analyze the wave pattern itself, okay, to get the respective R and C. Earth wire 26. Earth wire is quite easy. Okay, earth wire protects definitely the user. Okay, the user using the appliances. Now for question 27. Okay, question 27, there are a few factors that we need to analyze. Okay, so now based on the question is that there is a diameter differences. Okay, so there's the difference in diameter. Y is actually half the diameter. Now this information will lead us to the first information, that is resistance is rho L over A. And the area that we're looking at in this case is actually a diameter. I can safely assume it to be area equal to D squared over 4. Now, why d squared? Because we're looking at diameter, area is pi r squared. So that's where there's a divide by 2, and when I square it, there's a 4 there. Also, in other words, we are saying that r is actually proportion to 1 over d squared. So which means that when you have a higher diameter, the resistance of the particle, resistance of the cable will actually decreases. So in this case, whereby you look at ry, you will look at the cable y, you look at wire y, to be exact, diameter y, okay, is actually half of diameter x. This will tell us that actually the area will be 4 times. Okay, the difference of 4 times, and which means that the resistance will actually be a difference of 4 times. So in other words, we can actually safely say that because the diameter is half and area is actually what we call d squared. There's a d squared here. So I can actually safely say that resistance of y is actually 4 times of Rx. Okay, because what happened is the smaller your resistance, okay, the smaller your area, the bigger is your diameter. So dy happens to be a smaller diameter, or wire y happens to be a smaller diameter by half, as compared to wire x, which means that the resistance for y is actually 4 times as large as wire x. Okay, so now ultimately we will know that the current of y, okay, if you look at it, the current of y will actually be 1/4 times of x, because we know that current and resistance and current, the bigger the current, the bigger the resistance, the smaller is the current. So when your resistance is 4 times, okay, the current will be a quarter, quadruple, will be 4 times lesser. Okay, so this is the difference between, this is the relationship between the resistance and the resistance and the resistance and current. So if you rearrange the formula, you'll find that Iy is actually 1/4 of Ix. In other words, it will mean that, okay, the current, okay, Ix over Iy is actually 4 times. Okay, you bring this over, it will be 4 times. Okay, so in other words, if you're looking at the relationship between the two of them, you'll find that the current Iy and Ix, the ratio is actually 4:1. Okay, so the current inside Ix is actually, current inside Yx is actually higher. How much higher? 4 times. Okay, so this is what we mean by the changes in the wires with respect to the resistance itself. Now after working out that Ix over Iy is 4, okay, so you'll know that the current X is actually 4 times as Y. So you'll know the answer is D. Okay, so with this, okay, students, for this question, you may want to take a second look at this question to analyze the different factors that is given in the question. For this question, personally, right, I actually spent quite some time on this question because I was puzzled with the diameter, the difference in diameter, who has a higher resistance. After that, who has a higher wire current flowing through in due to the resistance changes, which due to the diameter changes. So there's like 3 layers of changes that we are looking at. Okay, so please be careful when looking at this question. 28, nothing major. 28, they still work on the same principle that resistance, current, they are related. Okay, in the sense that what we are looking at is the resistance of the resistance will increase, okay, and current will decrease. Okay, based on this factor. So when we say we arrange in terms of the magnitude of the current, okay, from descending order. So which means current wise, it has to be order. We are looking at descending order, so it will be big to small. In other words, I'm actually looking for resistance, okay, that is ranging from small to big, okay, because the bigger the resistance, the smaller is the current, and vice versa. Okay, so the smaller the resistance, the bigger is the current. Okay, so when the question asking for current, actually based on the question is that you have to analyze it from the resistance perspective. Okay, so from here you should be able to work out which is bigger. Okay, if you have problem like looking at it at like without values, you can actually give a number to it. Okay, example, you can give each of the resistor to be 10 ohm, 10 ohm, 10 ohm, 10 ohm. Okay, so if it's numbers, it can tend to make like the unknown like known, so it's like not so complicated, not so daunting. Okay, so you might want to look at number. Okay, since everybody's identical. Okay, so just take note of this. Okay, now the second problem is the option Y. Okay, here option Y, you find that some of us will tend, hey, how come I got so many resistance, but upon analysis, how come my wire is actually my Y is actually option Y is actually having the largest current, even though there are resistance inside. Okay, one of the things that students have to take note is that for option Y, you have to take note there is a line here. There is a line here. This line is actually the short circuit line. Okay, so which means with this line the presence of this line, it will imply that this line is actually perfect wire, which is resistance equal to 0 ohms. Which means with this line, no current will actually flow through this particular path. No current, because you have a path of 0 resistance. So all your current will actually flow down all the way to the last path, and it will go through this path only. Okay, the rest of the resistance path they will actually ignore, because the green color path is actually the path of the least, to be exact, is the 0 resistance. Everybody will run through it. Or sometimes we call it short circuit. Okay, so that's why I know actually with this, I will know actually B is actually the answer already. Okay, so we are looking at the numbers. So if you are sharp enough, you'll find, I will be able to derive at Y, the option B, okay, just by looking at Y itself. Okay, if not, you can look at it mathematically. You try to solve it. Okay, then you should be able to arrive at the same answer also. So there are some tricks in doing this question, the short way and the long way. Okay, so just take note of this. Now, for question 28, okay, 28, we are looking at the resistance, the current in the 5 ohm resistance, okay, 5 ohm resistance, which is here, and the value of the R here. Now, one thing for sure is that the easiest way to look at it is in terms of solving the circuit itself. So what we are looking at is actually I will want to combine this resistance together as a single resistor. Okay, so I'll combine these two resistors into this circuit. Okay, this R parallel. Okay, and with this, okay, the circuit remain the same. This is 3 amp. This is 25 volts. Okay, so once I sum up the resistance, okay, you'll find that this resistance, this R parallel, it will be actually 10 over 3 ohms. Okay, sum of resistance in parallel. So indirectly, I'm saying that the current, okay, the VR and VR parallel. Okay, so indirectly, because they are in series, okay, I will know that the EMF is actually VR plus VR parallel. Okay, because they are in series potential difference tend to add, you can add them together. So this will be IR, this will be IR parallel. So this will be 25 volts EMF based on the question. I is 3 amp, R is unknown, okay, plus 3 amp, and I know the resistance parallel, effective resistance for the parallel branch is 10 over 3, EMF is 25. So with this, you actually can solve for R already. And straight away, you'll know that R is actually, after solving the math, you'll know that R is actually 5.0 ohm. 5.0 ohm. So the answer here will be either B or C. So now let's look at how do we find the current inside? Okay, how do I find the current inside across 5 ohm? Okay, now based on the question is that if you look at VR parallel, okay, VR parallel, okay, so you look at the circuit, VR parallel is actually equal to I times R, okay, R parallel, which means that the 3 amp and 10 over 3 ohm, this will be actually 10 volts. So VR parallel is actually 10 volts. In other words, okay, since VR parallel is actually here, remember for parallel branch, the voltage across parallel branch is actually the same. Okay, since we know VR is 10 volts, so which means I am saying that because VR is 10 volts, inherently means that potential difference across this branch is 10 volt. Potential difference across this branch is also 10 volts. Okay, and from here, I should be able to calculate what is the current flowing through the 5 ohm branch, because V5 is actually 10 volts, resistance is 5, and from there I can work out the current to be 2 amp. And that's why I know the answer will be C itself. Okay, so this is, for this question, you still need like a few steps of working, so you still need some time for this. So remember, for students, you must, for take note is that for paper 1, there are actually 40 questions which you have to complete within 1 hour. So time is actually fairly demanding. Okay, so you have to take note of what are the fastest way or what are the most efficient way of doing it. Okay, so you can actually complete 30 questions in 1 hour. Okay, now potential divider question. Okay, I want what is the R resistance of R increases. Now, as resistance of R increases, okay, although it's in parallel branch, okay, but because R is increasing, so which means that the R parallel will also be increasing steadily, okay, increase bit by bit. And we say R parallel is increasing. I'm also saying that if resistance of R parallel increasing, which means that the voltage across it, V parallel, will also be increasing. Okay, so V2 is actually V parallel. So this is what we call V2. Okay, so V2 will actually be increasing. And indirectly, when we look at potential divider, is that we also know that the potential, the EMF here is actually finite. It's actually a constant value. And your EMF here is actually controlled. EMF is actually controlling the potential difference across V1 and also controlling potential difference across V2. If V2 is increasing and EMF is constant, okay, so for this case, EMF is actually V1 plus V2. So if my V2 is increasing and knowing that EMF is constant, it will mean that V1 has to decrease, okay, because to maintain the constant EMF value. So which means while V2 is increasing, V1 has to be decreasing. So that's why the answer here is B. Okay, so just take note of the when we look at potential divider is not just looking at the output or the V2 alone. Okay, you have to analyze what happened to when V2 changes, what happened to the V1 and what happened to the EMF itself. Okay. 31 will be a straightforward question. The color code for the 3M fuse. I will not run through this. Okay, but students, you have to take note. You have to remember the color code is it's all physics or what you call electrician's bread and butter. Okay, which question will distinguish magnetic and non-magnetic? Of course, magnetic, non-magnetic. The main thing about when you look at magnetic material, when you look at magnetic effect, okay, or magnetic field. Okay, the factor that investigate magnetic field line will be actually the usage of the compass needle. Okay, whether the compass needle actually points to the magnetic field lines. Okay, so this will be the questions that we are looking at. We should look at when we're looking at whether the object is a magnetic material or not magnetic material. That's why straight away option D. Now, question 33, when the magnet is in this field line, what will happen? Okay, so now the question students you have to ask yourself is, what do you mean? What do you understand from field lines? Okay, when we say the magnetic field is coming in this direction from bottom up, what does this represent? What does this tell you? Okay, so we go in the basics that magnetic field lines is actually denoted by leaving North Pole and entering South Pole. So when we say that the field line is coming from the bottom up, so which means that the bottom is where actually the North Pole will be. It's going upwards, so which means it's going towards the South Pole. So inherently, I can actually say the top is the South Pole, bottom is the North Pole. So what we are looking at is, okay, the north is at the bottom, the south is at the top. And after that, you take a look, when we have opposite pole, they will attract. So which means my South Pole will be attracted downwards. Okay, opposite pole attract. Okay, North Pole and South Pole. So my North Pole will actually go upwards. Okay, so which means inherently my magnet, okay, will actually rotate anti-clockwise 90 degrees. Okay, the South Pole here will actually come down. The North Pole will actually go up. Okay, so aka the pole will actually turn anti-clockwise 90 degrees. Now, the question 34. Okay, question 34 is a classic example of your magnetic field lines. Okay, now thing to take note is the drawing. Okay, this drawing denotes that the compass is below the wire. Below the wire. This is above. Okay, this is above. Okay, so other than that, I will not say this question is of any I would say this is not difficult. Okay, it's actually quite easy. Okay, it's a basic magnetic field line. So if I won't go through much because the 34, if you know the basic magnetic field lines, your Maxwell right hand rule, you'll find that the field line that the answer that you're looking at will be actually option C. Now for 35, okay, for question 35 here, you have to take note is we are looking at your Fleming left hand rule. But what's different is that instead of giving you a current, the question actually gives you the stream of electrons. Here you have to take note is that the direction of current is actually opposite, okay, to the direction of electron flow. Okay, so this is the two things. This is the thing that you must be careful. So in other words, we're also looking at direction of current is actually same direction as my proton. Okay, so these are the things that you have to be careful. Same direction as proton. My current direction is actually the same direction as proton flow or proton stream. My current direction is actually opposite, okay, to the electron stream. So in this case, when we're looking at Fleming left-hand rule, okay, if I have an electron stream that's going from right to left, this will denote that the current that my middle finger should actually point in opposite direction. Okay, my middle finger should actually be pointing to the right side. So when you use your left hand rule, you'll find that your middle finger should actually point towards the right side, not left, okay, because it's opposite direction. In addition, okay, my north pole is at the bottom. So field line always travel from north to south. So my field line is actually going upwards. Okay, if you use your Fleming left hand rule, your middle finger must point to the right, the index finger point up. You let go of thumb, you'll find that the thumb will actually point out of the paper, or aka the force induced will actually be pointing out of the paper. Okay, so that's why my answer is D. Okay, here the question I highlight again, please take note of the direction of electrons, protons, and the direction of current itself. They are like different, but they are related, okay, in terms of the meaning. Question 35, DC motor. Okay, DC motor, split ring, all this. Okay, which of the following will not increase? Okay, will not increase the turning effect of the coil itself, will not increase, will not increase. In this case, okay, you'll find that the easiest, sometimes I find that the easiest is to actually eliminate choices. So I increase the voltage supply, yes, definitely. If I increase the voltage supply, means the direct current will increase, and based on Fleming left-hand rule, current is one of the factors. So with current increase, the force induced will actually be increasing, and aka the turning effect will increase. Stronger magnet, definitely. Magnetic field lines, okay, will increase. My force induced will actually increase. Increase the diameter of the wire. Okay, increase diameter of wire, you have to take note. Increase diameter of wire, okay, based on the fact that resistance is rho L over A. Okay, if I increase my resistance of diameter of the wire, I'm actually looking at decreasing in resistance. So which means when my resistance decrease, my current will increase. So in other words, option A is actually trying to tell you that he's trying to increase the current. Okay, so he's trying to increase the current. And when current increase, and based on Fleming left-hand rule is one of the main factor, okay, the force induced will actually increase. So option A, B, and D will actually change. I already changed the turning effect. So you only left with one option, option D. And true enough, option D, removing a soft iron core. In this case, the soft iron core doesn't really affect because the field line is actually going to right to left. So there, as in I will use the iron core to actually concentrate the field lines. But in this case, because I'm using a bar wire, a bar magnet, sorry. So which means the field lines, I would say, is fairly concentrated at short distance. So that's why I will also say that C is also not one factor that will affect the turning effect. But of course, if in doubt, okay, you can look at what I did just now. I go through by elimination, by eliminating the right answer first. Okay, then I will end up with the only one and only answer, which must be the correct answer here. So once I eliminate A, B, and D, C will definitely be the answer itself. Okay, now we are at question 37. Is on Faraday and Lenz's law. Now, based on the question, first thing first, I'm pulled away slowly, and the deflection is to the right. So what happens is when I move away slowly, my pole induced, I will actually become a north pole here. Okay, so I become a north pole here. Why? Because I want to attract the south pole back. So in this case, you will find that south pole is on the right, north pole is on the left. So based on your Maxwell right-hand grip rule, you'll find that the current is actually going upwards this way. So which means my current is actually going from right to left in the setting here. So which means based on the red color button here, red colored arrow, you'll find that for my direction, okay, based on the question is if the current is going from right to left, the deflection here will be deflecting to the right. Okay, so let's get some direction first. If I'm going from right to left, the deflection will be to the right side. Now, what happened now is when the question says that it's move quickly towards the same end. Okay, there is two conditions in this case here. First thing is move towards. Second is move quickly. So we settle one thing at a time first. Now, what happened is when I move towards the coil, denote by green color. So now when I'm moving in towards the coil, my south pole is approaching. So what I do is my induced pole will be such that I will actually induce a south pole now on the left side. Okay, so now why is the south pole? Because the south pole is coming in, so I want to deflect it away. So what happens is I will become a south pole, okay, at the left hand side. So because opposite same pole, I would repel them. I will push the south pole. I will try to push the magnet away. So if I have a south pole induced on the left, I will definitely have a north pole induced on the right. And based on your Fleming Maxwell rule, okay, you'll find that now the current flowing in the coil is actually downwards. Okay, so the coil is actually flowing downwards. Okay, so you have to take note of the current direction. Okay, so which means in this case, the current on the left side is actually going from left to right. Okay, so take note of the green color direction. Okay, so if red color, right to left is deflect right. So now if I go from left to right, it will definitely deflect left. Okay, so at this instant, if I'm moving towards the coil, my ammeter will actually deflect to the left. Now, the second question I'm looking at, the second factor that I'm looking at is actually the coil move faster. The magnet move quickly. Quickly in the sense, it has the meaning of it is actually much faster than previously. So which means in this case, there will be a rate of change, or there will be increase in the rate of change of magnetic flux, okay, or your magnetic field lines, okay. And what happens is when you have increased rate of change of magnetic field lines, your EMF induced will increase, and when it's a closed loop, your current induced will increase. And your current induced increase, it will mean that the deflection actually is higher now. Okay, so in this case, for this particular question here, there is actually two conditions, okay, based on this statement, moving towards the end quickly. Okay, so you have to take note is for students, you need to take note of the two conditions here is to move towards the coil. Second condition is actually move quickly, move faster than previously. Okay, and this you will couple these two conditions, you will find that the deflection of the seen in the ammeter, it will be actually to the left, and the answer here will be bigger deflection. That's why the answer will be A itself. Okay, so take note of the slight clue or small clues that the marker is trying to give you, okay, so that you can actually work your answer out. Okay, now question 38, the AC generator, dealing with the location. Now here you have to be careful. Okay, when we teach AC generator, we always emphasize to students is that the induced EMF graph, okay, the EMF time graph, actually, other than telling you the factor, the time, the periods, the magnitude of the EMF induced, it actually also tells us the location of the coil itself. For example, if I know that, for example, at this point at the top here, at the peak, it's actually trying to tell us that the coil is having the largest rate of change of magnetic field lines, and it actually has the largest EMF induced. In other words, it's actually trying to tell us that the position of the coil is actually horizontal at 0, whereby the EMF, the rate of change of magnetic field line is 0. It actually tells us that the coil itself is actually vertical. A different position of the EMF graph actually tells us the position of the coil itself. So which means for position M will be the transit is in between the top, the blue, the black and the red dot. So which means it's a transition from the horizontal to vertical. Okay, so transition from vertical is already moved already. It's not at horizontal position, but it's transition from horizontal to vertical. Okay, so that's why I know the answer will be C. Transition from horizontal, already moved from horizontal in transition to the vertical column. Okay, to the vertical coil itself. So remember the EMF where the peak, okay, and the trough and the 0 point. Okay, the peak and the 0, okay, will actually denotes the location of the coil itself. Okay, so you have to take note of what the question is trying to tell you. What are the clues that's hidden inside this EMF time graph? Okay, other than the period and the amplitude of the EMF induced, the induced EMF graph also tells us the position of the coil itself. Okay, so that's why I know the answer here will be C. Now, question 39. Question 39 is a CRO question. Okay, as in CRO, rather than using the formula, I will actually rely on the basic of EMF, basic of the principle of CRO by looking at the time axis, by looking at the period of the graph itself. So for example, now I have a 20 volts, okay, peak voltage. My Y gain is 10 volt per division. Now these two information will tell us one thing. Okay, one division is 10 volts, so which means at 20 volts, I will actually have 2 square from the equilibrium position. Okay, so which means from equilibrium position, I will definitely have 2 square here because 1 square is 10 volts, so I will definitely have 2 square here. So which means any option with 2 square, that's my answer. So which means B and D is out straight away. Okay, between option A and C actually denotes that the waveform is actually 20 volts. Okay, 20 volts, remember, is always measured from the equilibrium position. Now, hertz, 10 hertz. Okay, so this will actually tell me that the frequency of my wave itself, frequency of the wave is actually 10 hertz, or sometimes we call this the period of the wave is actually 0.1 seconds. Now, time base, okay, so now when looking at time base, remember the first thing you do is I will always want to count the number of squares. So there's 1, 2, 3, 4, 5, 6, 7, 8. 8 horizontal square. And based on the question for time base is 25 milliseconds per division. So basically, I'm saying that the one square is actually 0.025 seconds. So if I have 8 square, okay, or to be exact, okay, if I have 8 square, I'm looking at, so if I have 8 square on the horizontal side, I'm effectively saying that 8 square, 1 square is 0.25, 8 square is effectively 0.2 seconds. Okay, so 8 square is 0.2 seconds. And based on this information, if you couple this information, horizontal 8 square is 0.2 seconds. One wave is 0.1 second. So effectively, these two information, I will be able to derive that I can actually see 2 wave, 2 cycle on the screen, 1 cycle, second cycle. Okay, so these 2 cycles. So that's why with this, I will choose my option to be A. Okay, A will be only one that matches all the condition. Okay, so this is normally how I use CRO. I will look at it from the basic point of view to look at how many squares I have, what's the time taken for the graph to for the CRO to sweep from left to right. Okay, so in this case, it will be actually 8 square. 8 square will be 0.2 seconds to sweep 1 cycle. So my wave is 0.1 second and 1 sweep is 0.2. So definitely I can portray 2 waves first before I start sweeping again. And from there, I will be able to derive at the answer. Okay. Question 40. Question 40 here. Same thing. This is what we call your AC generator. Now, AC generator, in this case, take note of this. The current here. This is the current of the coil. This is the current of the induced current. Now, and the magnetic field, just take note, is north to south. So it's going to the right side. Okay, so this is a green color one, denote the field line. Now, this is AC generator. AC generator. AC generator means the first instinct you are looking at should be your Fleming right-hand rule, not your left-hand rule. It's a right-hand rule. So between your right hand, and in this case, your index finger, your field line is actually pointing to the right side. Okay, and the middle finger, the induced current is actually pointing outwards. Okay, let's say we look at the left-hand coil. Okay, its field line, index finger is pointing to the right. Your field current is pointing outwards, and you will know that straight away the force acting on the coil itself, on the left coil, is actually downwards. Okay, this is the force itself. Okay, so if the left side coil is, the force is downwards, automatically you actually can assume that the force on the right side is actually upwards, or what we call the coil is actually rotating anti-clockwise. So it's looking at anti-clockwise, and I'm looking at it from the right hand perspective. So that's why I know my answer straight away is D. Now with this, this is the end of this paper. Okay. If similarly, okay, if I miss out any questions, or I have explained anything wrongly, or if there is any shortcuts that you would like to share with me, okay, please drop me a message, okay, at the comment bar below, or drop me via email so that I can actually get back to you, or I can just share your knowledge with my students, okay, so that we can all level up from there. Okay, if not, if you need a paper 1, I will leave the link on my top hand right bar in case you need a paper 2, sorry. Okay, so other than that, okay, I do hope I will be uploading some papers or some reviews on certain topics, especially with the new syllabus. I'll be uploading some videos regarding to the new chapters or some keywords that I actually encounter along the way with my students. Okay, if not, okay, this is where I end off. Okay, remember to subscribe to my channel and activate the bell button, to press the bell button so that you actually get notification for whenever I upload new videos that might be of interest to you. Okay, and I hope this video will actually value up your learning in physics, and hopefully making the learning of physics journey easy and smoother one. Okay, if not, okay, see you in the next video. Bye bye.